2. Calculus of vector valued functions. So now in this section, we're going to go over differentiating vector valued functions and integrating vector valued functions, both indefinite and definite integrals. All right. Again, this is not going to be anything really new other than putting this into vector context, right? The methods of integration are the same. We're not going to discuss any new differentiation or integration techniques. So the idea is that we have some vector valued function like we discussed in the previous section, in the previous very short section. And so that defines the position of the particle at a given time. If we take the derivatives of each component, everything is just going to change to prime notation. And what do? Differentiate. All right. And of course, this definition extends to the vectors in 3 dimensions, the vector values in 3 dimensions, and so of course, there's a special meaning about the derivative of a vector valued function. So just like in Calc 1, the derivative of a function was the slope of the tangent line at that given point in a function. So in this case, this is going to give us the tangent vector in the direction of increasing values of t. All right, so very similar. So derivatives of functions, slopes of the tangent line, derivatives of vector valued functions, the set of tangent vectors. And of course, just like we discussed at the beginning of the semester in the first section, we discussed the unit vectors, so the unit tangent vectors, which actually we will use a lot later in the course. What all we do is differentiate, or rather divide, every component of the derivative of the vector valued function by its magnitude, in the same way we did it with vectors with only numbers. So how about we go over one example? So we're given this vector valued function r of t, 4t minus 1 plus ln of t plus 4e to the negative 3 tk. And they're asking us to compute the derivative of the vector valued function. These are very straightforward differentiation problems. The derivative of 4t minus 1, which is just 4i. What's the derivative of ln of t? 1 over t in the direction of j. And the derivative of the exponential, which is itself e to the negative 3t times negative 3. We multiply with the 4. Is that a negative 12? And that's it. All right, that's it. For letter B, how about we find the unit tangent vector? So this t, the uppercase t in bold case, means unit tangent vector, and that's the derivative of the vector valued function over its magnitude. All right, we already got the numerator in the previous part. All we need this time is to find the magnitude. I'm going to do this below so I can save some space over here. So the magnitude r of t will be the square root of the f component, that is 4 squared plus 1 over t quantity squared plus negative 12 e to the negative 3t quantity squared. Okay, so that's going to give us a 16 plus 1 over t squared. And what are we going to have? 144 e to the negative 6t. All right, recall that when we have power of another power, exponents multiply, and negative 3t times 2, that's going to give us a negative 6t. So what are we going to have in here? Just divide our r prime. That's and I'm going to change these to component form. So you will see me going back and forth this time between linear combination of ijk and vector component. So that's going to be 4 1 over t comma negative 12 e to the negative 3 t, and we divide by the magnitude, which is this crazy radical here, 16 plus 1 over t squared plus 144 e to the negative 6t. And no need to simplify anything. Okay, we can just leave it. That's fine. But on the exam, you will. Just kidding. No, just it's fine. I mean, yes. I mean, no. There's really not much we can do. Like no, yeah. Letter C. They're asking us to evaluate the second derivative of the vector valued function and evaluate it at 1. So how about we first find the second derivative, r double prime. So the derivative of the first component, that's a derivative of 4, that's 0. The derivative of 1 over t, okay, how about we change that 1 over t as t to the negative 1. So the derivative should be, isn't that negative t to the negative 2? And then the derivative of this exponential, 12 times 3, that's 36. Negative times a negative is positive, 36 e to the negative 3t. And well, so all you might want to do is rewrite that negative exponent. I mean, again, there's really not much to simplify here. So that's the second derivative of the vector valued function. Now we are ready to evaluate that second derivative at the corresponding value. In this case, we want to evaluate it at 1. Wherever you see the letter t, substitute with a 1. That's all we do. Well, the first one is a 0. There's really nothing to substitute, or rather, there's nowhere to substitute. Negative 1 over 1 squared, comma 36 e to the negative 3 times 1. And well, that's 0, negative 1, and 36 e to the negative 3. I know, we're starting to get vectors with different numbers finally, because now we're generalizing to every kind of function, no longer linear functions in parametrics, and now we're incorporating everything. And well, another operation they're asking us to do, and well, this will have a special meaning later as we move on. Well, as we move on through this topic. So the dot product between the first derivative and the second derivative. So all we do is write down this vector. So the vector, which is the first derivative, which is this one right here, that's the derivative. The one I just circled, that's 4 1 over t and negative 12 e to the negative 3t, dotted with, make this smaller, dotted with the second derivative vector, which is this one right here. Let me circle it. That's our second derivative, and that's 0, negative 1 over t squared, 36 e to the negative 3t. Okay, and well, to find the dot product between two vectors, we multiply component by component. So number 1, 4 times 0, that's going to be 0. 1 over t times negative 1 over t squared, isn't that going to be, well, you know what, let me do the one step at a time. So 4 times 0 plus 1 over t times negative 1 over t squared, and plus negative 12 e to the negative 3 t times 36 e to the negative 3t. And recall that the dot product between two vectors is not another vector, but it's a scalar in this case. So 4 times 0, which is 0, minus 1 over t cubed, and 12 times 36, I have it to be negative 432. E to the, well, we have the same base, which is e. We add the exponents when we multiply this to be negative 6t. And that's the dot product of the two vectors. And well, just briefly, yes.
If the exponents have the same, like both of them have a negative sign, so the remaining can be positive.
Oh, but in this case, since, well, yeah, that's a good question. Let me write it in a different color on the side, like e to the, whoops, negative 3t times itself. What we do in this case is e to the negative 3t plus negative 3t. So negative 3 minus 3 is, yes, it's an addition of negative terms. All right, let's move on through this. So really, before going to the next topic, well, so later we're going to discuss how the derivative vector and the second derivative vector has very important applications, in the same way that when you took the derivative of a function in Calc 1 and then the second derivative function, the first derivative described the velocity of the particle moving along that graph f of x, and the second derivative described, what's that? The acceleration. So in this case, well, we're going to have systems. We're going to describe systems of position vectors, velocity vectors, also this calculating the speed, and in the end, we're going to look at these acceleration vectors. All right. So in the meantime, let's discuss other differentiation properties, in particular product rules. In fact, there's 3 different product rules for vector valued functions, and and when we multiply them, they're the same. The derivative of the first times the second plus the derivative of the second times the first. That's the same, except that in the one of the first 3 cases is a scalar function times a vector function. That's just a regular product rule. Then we have the derivative of a product defined by a dot product. So in this case, that's the dot product rule. And when we have 2 vector valued functions by the cross product, well, that's the cross product rule. But essentially, it's the same mechanics. It's just how we perform the product between the 2 vectors, or like in case number 1, it's a scalar function times a vector function. Well, let's do one example of number 1. And well, in this case, well, so we have the derivative of ln of t times the vector valued function u of t squared. And be careful here about how this is, how this is defined. So okay, give me 1 second. And then I need something here. Yes, okay. So, all right. So, the derivative of this product. This is the derivative of ln, and this is actually a scalar function and a vector here. So, in this case, this will be the derivative of the first factor, the derivative of ln of t, which is simply 1 over t, times the second factor, which in this case it's a vector u of t squared. All right, plus the derivative of the second factor. Well, in the first place, what's the derivative of u? It's u prime, right? U prime of, in this case, t squared. But notice how this is composed. This is not just u of t. It's actually u of t squared. What's the derivative of t squared? We would need to multiply by 2t. And that times simply ln of t, So, it's like it's the chain rule. No, I don't know if you if you've ever looked at chain rules, have you seen those nested dots or the babushka dots? Did I show you those here by any chance? Well, I have some of them. Well, they're not babushka dolls, they're Star Wars one, right? So, and you can always think of these composite functions as multi-layer functions. You know, we have an outermost function, which is the u, and an innermost function, which is the t. So what we do is differentiate the outermost function, and then inside we have an innermost function. And if we have a more complex function, we just take derivatives and derivatives of inner functions. This is how the chain rules work, right? I mean, they're kind of small. I don't know if everyone is able to see, but hopefully you get the gist of it, right? So that's basically the chain rule, right? Well, this one is not a very complicated chain rule, but if you go back to Calc 1, you did some crazy ones. So let's just clean this up. I mean, there's really nothing else to simplify over here. Smoothness and differentiability. And well, this is again another concept that comes from Calculus 1. We might recall that a function is not differentiable when we have asymptotes, when we had jump discontinuities, but especially when we had cusps or sharp corners at those values of t. And well, it's the same definition, but all we do is add the vector valued function. So a vector valued function is smooth on an open interval I if the components f, g, and h are continuous and the derivatives are not equal to 0. So it's smooth. It's smooth for all those values that are not whose derivative are not 0 for each component on the interval. So let's look at one example. So that's going to take us back to Calculus 2 for a few minutes. We're going to have this cardioid, but you might remember those graphs of flowers and of heart. Remember those at the end of the semester in Calc 2? Well, but we didn't define those as a vector valued function, but now we're doing that here this time. So we're giving this cardioid actually in a bounded interval, not its whole domain. That's important. You'll see why in a second. So, and they're asking us to find, number one, to evaluate the first derivative at pi over 2. All right. So, and r of t, or rather r prime of t, vector valued function. All we do is take the derivatives of the components. The derivative of 2 cosine, that's going to be negative 2 sine. And the derivative of cosine 2t, that's number one, the derivative of cosine is negative sine, but times the negative in front of it, isn't that going to be positive? Plus, and then multiply by mini chain rule 2 sine 2t. Comma, the second component, the y component, the derivative of sine, which is cosine, minus 2 cosine 2t. All right. So that's the derivative, and all we do is evaluate this at pi over 2. How do we do that? Well, just plug in the value of pi over 2 for each instance of t. So negative 2 sine pi over 2 plus 2 sine 2 pi over 2, comma 2 cosine pi over 2 minus 2 cosine of 2 pi over 2. Okay, let's evaluate some trigonometric functions here. Well, number one, sine of pi over 2, that's 1, isn't it? Okay, that one is going to go to 1. And sine of 2 pi over 2, which is really sine of pi, isn't that going to go to 0? So that's 1. So 1 times negative 2, that's going to be negative 2. comma, the y components are going to be, well, cosine of pi over 2, that's 1. And cosine of, wait, no, that's 0, 0. And cosine of 2 pi over 2, which is cosine of pi, that's negative 1. But be careful, because this negative 1 times the negative 2 in the coefficient is going to be positive 2. Alright? So that's what's going to be. So again, in this case, evaluating a vector at a value, the output is another vector, not just a value like we did in functions f of x in Calc 1 and 2. All right, so for the next part, we're going to need calculator. Sketch the curve, draw both r of t and r prime of t, that is the tangent vector. So and to plot this vector valued function, well, we're going to use our number 1 mode. Make sure that we have rating mode and it's in parametric mode. So lucky for me, I already had it. Clear. And well, let's just type for x, that is 2. No, that's, well, I need a 2 cosine t, close parentheses for the t, minus cosine 2t, close parentheses. And that's 2 sine t minus sine 2t. All right. And let's see if we get the graph. Yes, that's a cardioid. All right. So that's going to be the cardioid. Maybe if we zoom a little bit, zoom in. No, not that much. Well, let's just go back to the graph. So let's.
Which one are you graphing again?
Okay, so going back to it's the function in the previous page. So in parametric mode, we type the function in the part of the function in the direction of I, and on the y the direction. Yes.
Could you go over how you put in parametric mode?
Oh yes, sure. So maybe I went too fast on that one. So you go to mode, and number 1, because we're working with trigonometric functions, make sure it's in rating mode. And just scroll down a few times until you get function, parametric, polar, or sequence. And then just make sure that the parametric is highlighted here. And then click enter. And second quit maybe. And just go back to our. So now when you click the y equals, you will have a set of two parametric equations, one for x and one for y. So we just type each corresponding component for this given vector valued function.
Thank you.
Yeah, my pleasure. So let's see. Sketch the curve, draw both r of t and r prime of t. The tangent vector, actually, I didn't type this part, when t equals pi over 2. Right? So number 1, let's draw a Cartesian plane. And let's draw the cardioid here. All right. So, well, in this case, they're asking us to draw both vectors. Number 1, the vector, and when, in this case, it's pi over 2, when t equals to pi over 2, and the original vector. So in this case, number 1, how about we evaluate the original function r of t, or rather at pi over 2. That will be, in this case, so the derivative of the previous function, let me zoom it out a little bit. Okay, so I can have it here, the derivative. Oh, it's not the derivative, it's actually on the original function, 2 cosine pi over 2, and minus cosine 2 pi over 2, comma, and in this case, I'm going to need space in here. And that's I need it. Sine 2 sine pi over 2 minus sine 2 pi over 2. So let's do the same calculation, and so that's going to be cosine pi over 2, that's 0. So that's going to go to 0. And cosine of 2 pi over 2, that's cosine of pi, which is -1, but times negative, that's going to be +1, right? And then sine of pi over 2, that's the one that is, it's going to go to 1. And sine of 2 pi over 2, which is the same as sine of pi, isn't it 0? So that's going to be 1 times 2, that's 2. Alright, so at this point, when t equals pi over 2, we are going to have this vector, this position vector, starting from the origin and in the direction of 1, 2. So that's okay, let me zoom in. So that's the position vector when t equals pi over 2. And well, at this same point, we are going to draw the vector evaluated at its derivative, which in this case it's going to be the tangent vector. And this tangent vector, which is going to go, by the way, in the direction of how we draw this cardioid, which in this case it's positive orientation or counterclockwise. And in this case, from here, from this point, we're going to count -2 units in the x direction and 2 units up. So it's going to be roughly this point. Or this vector.
Where did you say it was again?
So, from the terminal point of the position vector, from there we are going to count -2 units to the 2 units to the left and 2 units up, which is the derivative vector, which is the tangent vector. I'm going to label this as a tangent vector. Which is r given by r prime at pi over 2, which is the vector -2, 2. And this other vector, the one in red, this one right here, will be the position vector when r, not prime in this case, just r, is evaluated at pi over 2, which in this case is this one we got here. I'm writing it again. 1, 2. All right. So let's see. So for the second part of the problem, or rather the third part, for which values of t is a curve smooth? Well, so in this case we phrase this r of t is smooth for all values of t except at the cusp, or at its cusp. That is, when t equals to 0, which is when we start drawing the graph from 0 to pi. Well, right now we're not going to focus too much on smoothness of curves and all that, but we're going to do this later when we go more in depth into this type of function. So you'll see. So now, well, we already did some derivatives. Well, guess what's next? Integrals of vector value functions. All right, and in this case, well, we can use every single integral formula or method from Calc 1, Calc 2, even partial fraction decomposition. Remember those? Yes. Well, no, I don't think we're gonna do anything like really crazy. I mean, you already went through that, so. But how about we discuss this when we